Good evening and welcome back, class. We are in week 4 of semester. This is Living Systems 1 and tonight we're going to be looking at lecture 4, covalent compounds. So remember last week we said there are two major types of bonding, and certainly there's not only two types of bonding. And we looked at ionic bonding last week. Tonight we're going to look at covalent bonding. And of course, you may already know, or you may have picked up, that there are a lot more covalent compounds that we come across than there are ionic compounds. So let's get into tonight's lecture. And as usual, if you have any questions as we go through the lecture, feel free to unmute yourself and ask away or type something into the chat box. And of course, I do my best to check the chat box, but sometimes I do get too carried away with the lecture, so excuse me. All right, so covalent bonds result from the sharing of electrons between two atoms. And remember, that is very different to the ionic bonds that we talked about last week, where the ionic bonds come about from loss of one or more electrons and gain of one or more electrons by another atom, and this confers charges to those atoms. And where we have an atom that has picked up a positive charge and another one that's picked up a negative charge, so for example a positive sodium and a negative chlorine, or rather chloride, because now it's charged, then those opposite charges will attract each other, and that attraction is referred to as an ionic bond. All right, so that's very different to what we're looking at tonight. Covalent bonds don't result from loss and gain of electrons, but sharing of electrons between two atoms. And they may be the same type of atom, or they could be different atoms. And that's what we're going to look at here. So let's start with hydrogen. As you see it on the periodic table, hydrogen. Can everyone see what I'm drawing to the left of screen? Yeah. Good, thank you. All right, so we know that hydrogen sits at position number 1. In other words, it has the atomic number 1, and there it is there. And then you also know that, or you might know, or you do know if you look at your periodic table, that we have the mass number here, 1.01. And I'm just going to revise what these mean and then also give you some more important information about hydrogen, because it's really quite unique amongst the elements. All right, so what does this number 1 tell us? I want you to tell me, what does this number 1, the atomic number, what information does that give us? Number of protons, correct. In other words, a hydrogen atom has 1 proton. What else does it tell us? Assuming that the hydrogen atom is neutral, uncharged, 1 electron, correct. So that's telling us that there is proton equals 1 and electron equals 1. All right, now let's look at how we can round this number, round it down to 1 and use that also. And you might remember that we drew this sort of representation of hydrogen where we put the atomic number 1 down here as a subscript, and we put the mass number rounded to 1 here as a superscript. And from this, given this representation, we can now work out the number of neutrons. How do we do that? Tell me what I need to do now to work out the number of neutrons. What would you do? What very simple calculation would you carry out, given that information there, which is basically the information that you have here, but in reverse, because now the mass number is sitting up here, atomic number down there. What does that tell us about the number of neutrons? Okay, I think everyone's quickly referring to their notes from last week, or sorry, the week before. Subtract one from the other. Yes, minus the number of electrons. Yeah, not quite. All right, someone has said 0. That's correct. Number of neutrons is 0. We subtract one from the other. Which one do we subtract? Protons, that's right. So we subtract the number of protons, which is this number here, from this mass number. And that will give us the number of neutrons. In other words, 1 take away 1, 1 take away 1 equals 0. So here is the uniqueness of hydrogen, an atom of hydrogen. They generally lack protons. They consist of just that one, they lack neutrons. I warned you that I was tired. They lack neutrons. Correct. Thank you very much for correcting me, someone. All right, they lack neutrons. They have 1 proton and 1 electron. All right, so that's a good one to remember, especially for later on in one of our later lectures. That becomes quite critical to understand that concept. All right, so let me clear that. And let's go to work on what we see on this slide. All right, so hydrogen. We've established that hydrogen has 1 electron, and we can draw it like that, hydrogen with 1 electron. What other information does is on the periodic table that tells us that hydrogen has 1 valence electron? How would you know very quickly that hydrogen has 1 valence electron? Correct, the group number. So remember, that's really useful. We know hydrogen is in group 1A, which tells us it has 1 valence electron. And now you know hydrogen has 1 electron in total, okay? So here it is, hydrogen's single valence electron, and in fact, it's the only electron it has. Now, let's draw another hydrogen here with its electron here. Now, think about the electron configuration of hydrogen. It's simply 1s1. What does this 1 stand for? What does this 1 stand for? The first shell. So this is shell n equals 1, or shell number 1 if you like. What does this S stand for? What's that little S? The first subshell. Good, excellent. And what's this little 1 here represent? What's this little 1 up here represent? Okay, 1 electron. How many electrons? Yes, good, excellent. All right, outer electron, yes, which happens to be its only electron. Correct. All right, so that's its electron configuration. But what happens, let's look at what happens when hydrogen, 2 hydrogens come together and they share their electrons. In other words, we say that this hydrogen on the left is now surrounded by 2 electrons, and this hydrogen on the right is also surrounded by 2 electrons. That's right, we have what's called a covalent bond between them. So the sharing of those electrons is referred to as a covalent bond, and that's normally drawn as, that covalent bond is normally drawn as a single line in between the 2 atoms. So this single line represents a single covalent bond, and you assume when you look at that and assume correctly that that bond is made up of 2 electrons, 2 shared valence electrons, 1 coming from 1 atom and 1 coming from the other atom. Keep in mind that those electrons are not being transferred. They're not being transferred, different to ionic bonding. All right, now let's look at this again. So if we were to think about now the electron configuration for this hydrogen here, it would be more like this, wouldn't it? it would be more like this, even though it hasn't actually taken that electron from its neighbouring hydrogen, hasn't taken it, but what we see here is a completely filled shell, a completely filled subshell and a completely filled shell. And this happens to be a lot more stable, a much more stable arrangement than this here. Okay. So this is the preferred state, the more stable state for hydrogen. And that's why hydrogen as it exists in the atmosphere exists as such, as two hydrogens bonded together, and we call this a diatomic molecule. Diatomic molecule. And you'll notice that I'll probably start using the term molecule. Oh, my writing is getting worse. I'll start using that term molecule a lot more in this lecture. And you can see why down here. A molecule is a discrete group of atoms held together by covalent bonds. So last week we talked about compounds. This week I'll use the term molecule a lot more because we're describing covalent molecules. Okay, we have a question. Are CB, covalent bonds, always stable than ionic bonds? That's a very good question. Covalent bonds can be incredibly stable and incredibly strong, and I'll show you a good example of that a bit later on. Ionic bonds are also quite strong bonds depending on the compound. So I can't really generalise in regards to that question there. All right, so back over here. So this is how we normally find hydrogen, atmospheric hydrogen, or you can call it molecular hydrogen, and it's a diatomic molecule. What else do you think we would find in this way as a diatomic molecule in the atmosphere? Any idea? Diatomic, and of course if it was just one atom it would be monatomic. Oxygen, good. Oxygen's another great example. Oxygen, there we go. Yep, great. Another one is nitrogen. Okay. All right, so they're all diatomic, just some examples for you. All right, so what is a covalent bond? It's a 2-electron bond in which the bonding atoms share electrons. And the reason they share is because they are more stable, electronically stable in this configuration. That's not to say that's the only way they exist, but we certainly won't go into all the details. All right, we have another question. Can you explain why nitrogen and oxygen would be found like that? Yes, I actually will explain that in the next couple of slides. We'll actually go into both of those examples. So thank you. All right, now let's look at another example. Here we go. Another example of a covalent compound or molecule. And this example involves two different atoms. Here we go. Let's go hydrogen again. And we know hydrogen has one valence electron. What about fluorine? Let's go fluorine. Okay, what group number does fluorine belong to? What group number does fluorine? 7A. And what do we call the 7A elements? Group 7A, what do we call them? They have a name, which you should know. Halogen, good. These are the halogens in group 7A. And given that, how many valence electrons does fluorine have? How many valence electrons? Given that we know the group number, yes, 7. Good. Let's draw them. 7. 1, 2, 3, 4, Now we start pairing up 5, 6, 7. All right, who remembers when it comes to valence electrons, that magic number, that stable number that many of these main group elements are trying to achieve? Number 8, yes, number 8. Most of them, of course, not hydrogen. Hydrogen only wants 2. It's a bit different, it's the exception. But yes, 8. Remember octet. Remember the octet. Yep, so that rule also applies here. Octet. Fluorine wants 8. Yes, octet rule. So it can get that very easily by doing this. By sharing one of its electrons with the electron from hydrogen. It will share one of its electrons. Now let me just draw this. Okay, now let me just get a different colour. I never know which colour is good to use, but I will try different ones. All right, now let's look at what's happened. Hydrogen, oh, that's dreadful. Hydrogen has its desired 2. Oh, I'm going to change that colour. And let's look at fluorine. Let's look at fluorine. What's the situation here with fluorine? Fluorine is now surrounded by how many electrons? Remember, you always take into account the electrons in that covalent bond. 8. Correct. Fluorine has 8. It has achieved its desired octet. And that's what we see here on this slide. All right. So hydrogen shares its 1 electron, but it only wants to be surrounded, needs to be surrounded by 2 electrons. So remember this as the exception. Other main group elements, not all of them, there are exceptions, but many of the other main group elements are stable when they possess an octet of electrons in their outer shell. All right. Oh, and before I move on, these electrons here, these non-bonded electrons that remain on the fluorine, of course, they're simply referred to as non-bonded electron pairs or lone pairs of electrons. So given that you understand that, how many lone pairs of electrons are on this fluorine here? How many lone pairs? Okay, we've got a 3. Yep, everyone? Yep, everyone put your answer in the chat box, whatever you think. Okay, we've got another couple of 3s, 3. Okay, all right. All right, I get the message. Yep, you all understand that. Fantastic. Great. Let me clear that. Yep, 3 lone pairs. Excellent. All right, now, now we're going to look at Lewis structures. Lewis structures are simply electron dot structures for molecules. They show the location of all the valence electrons. Okay, and we're going to work through each of these examples just to give you some practice. And we're going to start with this one, methane. CH4 is methane. All right, let's draw that carbon, single carbon. What group number does carbon belong to? What group number? I hope you've all got your periodic table in front of you. All right, we've got a 4A, we've got a 6, we've got a 4. Oh, we've got 3 different answers at the moment. All right, come on, everyone. We've got a 4A, another 4A. All right, I think that's all that's coming in. All right, if you said 4A, you are correct. 4A, I just checked my table. Very good. It's very handy to have that table with you all the time. Group 4A. So what does that tell us about the number of valence electrons that carbon has? Okay, we've got a 4, 4. All right, it has 4. It certainly does. Let's draw them. 4 valence electrons for carbon. How many valence electrons does carbon want? It has 4. What does it actually want? It wants 8. So we've got an 8, a 6, an 8, an 8. It actually wants 8. Remember, octet. Octet. Okay, it wants 8. Yes. All right, now let's draw in the 4 hydrogens. So we'll put a hydrogen there. And we'll put a hydrogen there. And one here. And another one there. And now you can see if covalent bond forms there, and there, and there, and there. Now how many electrons are surrounding carbon? If it forms 4 bonds, correct. It now is surrounded by, it's now surrounded by 8. And that is the aim. All right, good. And of course, each hydrogen atom it is surrounded by 2 electrons. All right, excellent. So, so we have a Lewis structure for methane. That's exactly what we see here. And of course, here we have those covalent bonds simply drawn as those single covalent bond lines, which is how we normally represent these covalent molecules. All right, let's look at another example. I'll just clear that, and we're going to look at this one, NH3, which you probably now know is ammonia. All right, so what have we got? We've got a nitrogen, a single nitrogen here, single nitrogen. We have a question, which is the Lewis structure. So both of these are acceptable as Lewis structures, both, because they are both showing the location of all the valence electrons. Okay. All right, nitrogen. What group numbers does nitrogen belong to on the periodic table? Everyone, find nitrogen. We've got a 5A, 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 5A. Excellent. Yes. Very good. That's great. 5A is correct. Let's draw those valence electrons. 1, 2, 3, 4, and 5. How many does nitrogen want? How many does nitrogen want? Another 3, correct. Wants another 3 to satisfy that octet rule. All right, let's draw in our 3 hydrogens, and we'll use these single ones to form covalent bonds to a hydrogen, and here another hydrogen, and here to another hydrogen. Okay, now count those electrons that are surrounding the nitrogen now. And if you do that, how many electrons around nitrogen? And we have satisfied the octet rule. Excellent. And of course, each hydrogen is also satisfied with that full shell. Full shell, full subshell. All right, so that's nitrogen. How many lone pairs of electrons are remaining on the nitrogen? Okay, 1. You're all predicting my questions. That's great. That means you're really listening, or I'm just very predictable. All right, next example, water, H2O. Let's look at water. Oxygen, group number for oxygen. All right, 6A, 6A. Some of you are very quick at this. 6A, 6A, oh, look at that for predicting my question. 6A, and it needs another 2 lone pairs, another 2. Ah, you predicted 2 of my questions. So you're saying it needs another 2 electrons, and it will form, 2 lone pairs will be remaining. Now that's, yeah, that's pretty impressive. All right, belongs to group 6A. Let's draw them. And I'm tempted to go much faster, but I will resist because I know that I always get students saying, you go too fast. All right, so yeah, I do all the time, even when I think I'm going so slow. You know, there's always students that say that was just a bit too fast for me, and yeah, so I always have to keep that in mind. All right, so we've got 6 valence electrons. It wants an octet of 8. So that means we need to form, or rather oxygen needs to form 2 covalent bonds, which it does very happily with 2 hydrogens to form a molecule of water. And as someone said, we have 1, 2 lone pairs of electrons remaining. Great. And if you counted up the electrons surrounding the oxygen, you would see that there are 8, of course. 2, 4, 6, 8. Fantastic. And there we have it, 2 lone pairs there. All right, let's clear that and move on to the next slide. All right, so when do covalent bonds mostly form? They're formed between 2 nonmetals, or when a metalloid bonds to a nonmetal. All right, so given that, and given a range of different compounds or molecules, you should be able to determine which one would most likely have covalent bonds, or which one would most likely be an ionic compound. Always exceptions. All right, so that's covalent bonds, when 2 non-metals combine, or when a metalloid bonds to a non-metal. Some rules for you. How many covalent bonds will a particular atom form? So atoms with 1, 2 or 3 valence electrons generally form 1, 2 or 3 bonds respectively. We've seen some examples of that. Atoms with 4 or more valence electrons will form enough bonds to give an octet, and we've seen some examples of those. So the predicted number of bonds for a particular atom equals 8, take away the number of valence electrons. And I think you are all over that already, which is fantastic. All right, so let's look at the common ones, and I believe, yes, we've already looked at all these, but this is a really useful slide, very important slide to keep in mind, not just for this semester, but even for living systems too, when we get into the organic chemistry. This is equally relevant. All right, so hydrogen, group 1A, it has 1 valence electron. It forms 1 covalent bond with 0 lone pairs remaining. Carbon, 4A, as you know, so it has 4 valence electrons. It uses all 4 of its valence electrons to form 4 covalent bonds that you can see there. Number of bonds 4, number of lone pairs remaining 0. Nitrogen, okay, 5A has 5 valence electrons. It uses 3 of those 5 valence electrons to form covalent bonds, 1 lone pair of electrons remaining. So it forms 3 bonds, 1 lone pair remaining. Oxygen, group 6A. So it has 6 valence electrons. It uses 2 of those 6 valence electrons to form 2 covalent bonds with 2 lone pairs remaining, and hence the 2 and the 2. Okay, this is very useful for everyone to know. And then the group 7A halogens, where the halogen is denoted here by the letter X. 7 valence electrons for these ones. The halogen will use one of its 7 valence electrons to form one single covalent bond with 3 lone pairs of electrons remaining. So 1 bond, 3 lone pairs. Okay, students do get quite confused with these. I've noticed every year in the mid-semester test or no, not on the final exam, in the mid-semester test. So this is really a good one to revise. As I said earlier, even though the test is online, you know, you can have your notes with you. You really don't have time to keep referring to your notes. And I notice that as students getting confused with these ones. Okay. Great. All right, so just to wrap up on Lewis structures. So when we're looking at a molecular formula, such as CH4, H2O, and so on, that formula will show the number and identity of all the atoms in the compound, but not which atoms are bonded to each other. As we've just seen, a Lewis structure will show the connectivity between the atoms, as well as the location of all the bonding and non-bonding valence electrons. Here are some general rules for drawing Lewis structures. Draw only the valence electrons. Give every main group element, except for hydrogen, an octet of electrons. Make sure each hydrogen is only surrounded by 2 electrons. All right, let's look at an example of how to draw a Lewis structure. Step 1, arrange the atoms next to each other that you think are bonded together. Place any hydrogens and any halogens on the periphery, since, as you know, they only form one covalent bond. So for this example, CH4, we've got carbon in the middle and it's surrounded by 4 hydrogens. Look at this example here to the right and look at why that appears to be wrong. All right, so the answer, or one of the answers is here, that this hydrogen here can't form 2 covalent bonds. That just can't happen. But there's another reason why this is incorrect. Who can tell me why this is not right? What else would be wrong with this example here? Okay, so if we put a covalent bond there and there and there and there, carbon would have a spare electron. Yeah, that's true. You would have an electron sitting here. Yeah. Yeah, that's true. That is true. What else is not being satisfied here? You're looking at the right part of the compound here, the molecule. That's right. Yes. So look at carbon. It would not be surrounded by an octet of electrons. Absolutely right. Good. All right. Let me move on with this. All right, step 2, count the valence electrons. For main group elements, the number of valence electrons is equal to the group number, as you already know very well. The sum of those valence electrons gives the total number of electrons that must be used in the Lewis structure. So for this example here, CH3Cl, 1 carbon equals 4 valence electrons for a total of 4, 3 hydrogens, and you know each one has 1 valence electron, so a total of 3. 1 chlorine has 7 valence electrons, total 14 valence electrons that have to be accounted for in the Lewis structure. Step 3, arrange the electrons around the atoms, place 1 bond, that is 2 electrons, between every 2 atoms. For main group elements, give no more than 8. For any hydrogen, don't give any more than 2, and use all remaining electrons to fill octets with lone pairs. All right, here's another example for us. So still on the same CH3Cl, we've got our central carbon here. We put the 3 hydrogens on the outside and the halogen also on the outside here. All right, so if we were to count all the valence electrons, that's pretty simple. We've got 4 covalent bonds, each one worth 2 electrons for a total of 8. We've got 3 lone pairs on the chlorine for a total of 6 electrons. So we have used up all those 14 electrons. So that's pretty straightforward. And that brings us to the topic of multiple covalent bonds. So far we were looking at single bonds, but this is also very common, multiple covalent bonds. Let's look at this example here with these 2 oxygens. And let's demonstrate, let's illustrate rather why oxygen, diatomic oxygen, O2, why it actually needs a double covalent bond. All right, how many valence electrons does oxygen have? 1, 2, that's right, 6. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Let's just draw a single covalent bond between those 2 oxygens. Why is that wrong? Why is that wrong? What's the problem with a single? That's right, there's no octet. If we look at this oxygen to the left, it is surrounded by how many electrons? 2, 4, 6, only 7. And the same thing for this oxygen here. So if we do this, I don't need to draw it. If we do this, now you can see that each oxygen, let's look at this one, 2, 4, 6, 8. So now we have an octet for that oxygen, and the same applies for this oxygen on the right. Good. All right, let's do the same thing now for nitrogen. Okay, so nitrogen, N2, diatomic nitrogen or molecular nitrogen. How many valence electrons for nitrogen? How many? Oh, my virus protection is hiding. Okay, so we've got a few different answers here. Okay, 5. Yes, yep. A few people have said 5. Good. Good. Let's try that out. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right. So once again, if we only use a single covalent bond, here, each nitrogen would only be surrounded by 2, 4, 6. If we try a double bond, we would have 2, 3, 4, 5. Yep, 2, 4, 6, 7. So that doesn't work. All right. So hence the need for a triple covalent bond. And that's commonly how atmospheric nitrogen exists, with that very strong triple covalent bond. Can anyone tell me, and I think some of you have probably talked about this briefly in another subject, what natural event is powerful enough to break that triple covalent bond? What naturally occurring event is powerful enough to break that triple covalent bond in nitrogen? And by doing so, allow nitrogen to actually be washed down to earth, to the soil. Lightning, correct. Good. Okay, a couple of students have said lightning, and that is very true. All right, let me remove that, and we shall move on. All right, so let's look at an example, and this is just for your interest, an example of a Lewis structure with multiple bonds. So, example, draw the Lewis structure for C2H4, arrange the atoms with carbon in the middle, the carbons in the middle, hydrogens on the outside, count the valence electrons, 2 carbons, each one with 4 valence electrons for a total of 8, 4 hydrogens, each with 1 valence electron for a total of 4, total overall 12 electrons that need to be placed. All right, step 3, add the bonds and lone pairs. So in this example, we've got some single covalent bonds here, and carbon has a lone pair of electrons here. Okay, very odd place, isn't it? All right, so the reason that was done there, I would say, would be just to illustrate that all 12 valence electrons have been used. But of course, you can see already that there's a problem with that. And that is that the carbon, this carbon, does not have an octet of electrons. This one does, but not that one. All right, so the solution: to give both carbons an octet, change the lone pair into an extra covalent bond between the 2 carbons. In other words, take that lone pair and convert it into an additional covalent bond line, as you can see here. And now we have satisfied the octet rule. All right, as I said earlier, there's lots of exceptions to the octet rule. Most of the common elements will follow this rule. Hydrogen, as you know, is a notable exception because it needs only 2 electrons. But elements in group A also don't seem to follow the octet rule. And here's an example: boron, which only tends to be surrounded by 6 electrons, not 8. And here's another 2 exceptions to the rule. And this generally involves some of the elements in the 3rd row. So phosphorus is a good one. It can be surrounded by 10 electrons, and sulfur is another one, can be surrounded by 12. Okay, exceptions to every rule. All right, now let's revisit one of our polyatomic ions from last week. So if you've forgotten polyatomic ions, go back to last week's lecture and look at the very last slide. And we had some examples of common polyatomic ions. You can tell me what sort of bonds hold the atoms together in a polyatomic ion. What sort of bonds? So even though they are ions, the bonds between the atoms are not ionic bonds. What sort of bonds are they? Polyatomic ions. So we looked at examples such as, in that table, carbonate. That was one of your tutorial questions. We mentioned nitrate, nitrite, sulfate, sulfite, hydroxide, cyanide, which is the example we've got here. Can anyone remember the type of bond that holds the atoms together in a polyatomic ion? Okay, positive charge, monatomic bonds, ionic bonding. Okay, all right, good tries, we're not there yet. What type of bond holds the atoms together in a polyatomic ion? The answer is covalent bonds. Covalent bonds. These atoms are held together by covalent bonding, not by ionic bonding, but they're called ions because the molecule itself is charged overall. It carries an overall charge, net charge. So they're still referred to as ions. All right, let's see how that all works. And we're going to use this example that you can see here, cyanide, which as you can see has a single carbon and a single nitrogen and carries an overall net charge, a single negative charge. All right, so it's got one carbon for 4 electrons, total of 4. It has one nitrogen, which equals 5 electrons, and it has a negative charge. So given that it has a negative charge, we need to add 1 electron. All right, and there it is there, 1 electron for the negative charge. That gives us 10 electrons in total. If we actually draw a Lewis structure for cyanide as such, yeah, and we just use a single covalent bond, then all 10 of those valence electrons will be used, but carbon will lack an octet. But here we can see that with the presence of a triple covalent bond, let's count up the electrons now. 2, 4, 6, 8, 10. We've used up those 10 electrons in total. But remember, there is a charge because of the presence of this additional electron, and that's denoted as such. Okay, so this explains why cyanide has a negative charge, because that 1 extra electron is critical in order for this molecule to actually form. And this molecule is quite common in nature. Can anyone tell me in the plant kingdom, for example, where you would commonly find cyanide? Where you would find cyanide in the plant kingdom? Pips, yes. Cherry pips, almonds, yep. Yep, lots of different examples, correct. Okay. So let's clear all that. Okay, so once again, this is for your interest only. All right, let's move on to a completely different concept now, and that is naming covalent compounds. And you'll see that it's a bit different to how, in fact, it's very different to how we name ionic compounds, and much easier too. Students tend to find this quite straightforward. All right, so we've got 2 examples here. We've got NO2 and N2O4. Let's name the first non-metal by its element name. So that's easy. Here's the first one, and we simply call it nitrogen. And then we name the second element using the suffix "ide." So here we have oxygen. So oxygen becomes oxide. Let's look at this example. We've got nitrogen, and the second element is oxide. But of course, these 2 names are the same, describing 2 very different molecules. And that's where we use prefixes. So this is the big difference, or one of the big differences between naming covalent molecules and ionic compounds. When it's a covalent molecule, we use these prefixes to show the number of atoms of each element. We're going to use prefixes from the table on the next slide, prefixes like mono, di, tri, tetra, and so on. I'll show you that in just a minute. Now, this prefix mono, of course, meaning 1, is usually omitted. We don't normally use that prefix, but there are exceptions, as always. Here's a classic exception, CO. CO, we don't say carbon oxide, so we don't omit that mono. We do include it, carbon monoxide. Note here we don't say carbon monoxide, and that's because if the combination places 2 vowels next to each other, we omit the first vowel. In other words, mono as the prefix and oxide as the name of the element oxygen, then we drop one of those O's to give monoxide. All right, let's look at the common prefixes that we use in this naming of covalent compounds. So if it's 1 atom, mono, 2 di, 3 tri, 4 tetra, 5 penta, hexa, hepta, octa, nona, deca. I Always assure students that in tests and exams, I don't go higher than tetra, okay? So you don't have to go off and memorise the whole table, unless you want to, that is. All right, so that means we can complete our naming here. We have a single nitrogen in this example, so that's fine, but we have 2 oxygens, so we use this prefix dioxide. Nitrogen dioxide. Here we have 2 nitrogens here, so we say di-nitrogen. 4 oxygens, there's 4 tetra, but we don't say tetraoxide, drop the A, and that gives you tetroxide, dinitrogen tetroxide. All right, so that's fairly straightforward. And now we're going to very briefly cover this theory which describes the shape of molecules, the geometry of molecules. The theory is called VSEPR, valence shell electron pair repulsion. And it's based on the theory that the most stable arrangement for any molecule is that arrangement that will keep the electrons in particular as far away from each other as possible. And that's because electrons, of course, are negatively charged. They will repulse each other. They will repel each other, I should say. So that's just one of our laws of nature, I like to say. All right, so to determine the shape around a given atom or the shape of a given molecule, first determine how many groups surround the central or core atom. A group is defined as either an atom or a lone pair of electrons. So let's look at some examples. So any atom surrounded by only 2 groups will be a linear molecule, and will have a bond angle of 180 degrees. So here we go. Here's our central atom here, which in this case happens to be a carbon. Here are the 2 groups, one there and one there. They happen to be oxygen, 2 oxygens. All right, so they're the 2 groups. So we have a linear molecule, and here's the bond angle, 180 degrees. Another example, any atom surrounded by 3 groups is said to be trigonal planar and has bond angles of 120 degrees. So here's our example. We've got a central carbon, 1 group, 2 groups, 3 groups, 2 hydrogens and an oxygen. And here's our trigonal planar molecule, and also there. So once again, it's planar, so it's a flat molecule. All right, this one's a bit different. Any atom surrounded by 4 groups is tetrahedral and has bond angles of 109.5 degrees. So here's our example, CH4, central carbon, surrounded by 4 groups. In this case, it's 4 hydrogens. And here is an illustration of a tetrahedral molecule. So if we look here at this, this Lewis structure, you can see a couple of odd-looking covalent bond lines. So this one here that looks like a solid black wedge, that covalent bond line indicates that this hydrogen is sitting out in front of the plane of that carbon. This one here, this dashed covalent bond line, tells us that this particular hydrogen is sitting behind the plane of that carbon to form that tetrahedron shape. All right, if the 4 groups around the atom include 1 lone pair, then the geometry is trigonal pyramid with bond angles of about 107 degrees. So the example here is NH3, and you know that already is ammonia. So here's our central atom, the nitrogen. 3 groups here. The 4th group is the lone pair on the nitrogen. And I think this is our final example. If the 4 groups around the atom include 2 lone pairs, which is what we see here for H2O, water, then the geometry is bent and the bond angle is 105 degrees. So there's our bent molecule. All right, moving on to our last concept, and a very, very important one going forward for everyone. And this concept involves the term electronegativity. You've been very, very briefly introduced to this, but let's look at this in more detail. So what is electronegativity? It's a measure of an atom's attraction for the electrons in the bond. So for example, in that covalent bond. And it tells you how much a particular atom wants those electrons, or if we want to put that a little bit more scientifically, we can refer to that particular atom's ability to attract the electrons in that bond towards itself. All right, so one way of looking at this is to consider two atoms. Okay, two hypothetical atoms, and here's the bond line. Okay, so here's one electron and here's another electron. So both of these atoms, we can say, are equally sharing the electrons within that covalent bond. But that's not always the case. Let's look at another possibility. In this case, we could have something like that. So you can see very clearly that this particular atom is exerting a greater pull on these electrons. It's not taking that electron from this atom, not taking it completely, which is of course what happens in ionic bonding, but it is certainly drawing that electron closer to itself. All right, what about this example? Okay, so here's another possibility. Now in this example, this atom on the right is almost taking this electron completely from this atom here. Not quite taking it, but almost. Okay, so I think that's useful way of visualizing it for some students. All right, so once again, electronegativity is a measure of an atom's attraction for the electrons in a bond. So given that, which of these three examples, and just looking at the atom on the right, which of these three has the highest electronegativity? The highest electronegativity. Okay, I've got the third, yes, correct. So this one here, this particular example here, this atom has a much higher electronegativity than this one, and this one has a higher electronegativity than this one. Now, if we look at this table here, this is a great table because it contains these values. Values like 4, 3.5, and these are electronegativity values. You won't see these particular values on your version of the periodic table. Okay, they're electronegativity values. So if you just have a scan over this table, oh, and of course, let's look at the trends. There's some trends here. So if we go from left to right across a period on the periodic table, electronegativity will increase. And here's another trend. If we go from the bottom to the top of a group, then electronegativity increases. In general, they are trends. There's always exceptions. All right, so looking at this, at these values, electronegativity values, which one has the highest? I have got non-stop messages and phone calls coming through, as you can imagine. All right, which one? Fluorine, yes, very good. Fluorine has the highest in the whole periodic table with an electronegativity of 4. And then, of course, if you look over here, no, doesn't apply to helium. Helium doesn't form covalent bonds. The noble gases. The noble gases tend to exist as monatomic elements. Yep. They are very stable just the way they are. All right, think about helium. Helium, number 2. It occupies number 2. Occupies. It has the atomic number 2, which means it has 2 protons and therefore 2 electrons. Think about the electron configuration for helium, 1s2. It's already stable the way it is. Yeah. If you look at the other noble gases and use the same sort of line of reasoning, you'll see that they're also very, very stable. And that's why they're so unreactive. So unreactive. They can only be forced to react under very, very under experimental conditions in the lab. They can be forced, or at least one that I know of has been forced to react. Yeah, so they're very, very stable, the noble gases. Yes, that is correct. That's right. All right, so keep these electronegativity values in mind. Oh, let's just look at 2 examples. Keep this one in mind. Carbon has a value of 2.5 and hydrogen 2.1. All right, keep that in mind as we go to the next slide. All right, so now let's look at this covalent bond here between the 2 carbons. Carbon, as we just saw, has an electronegativity of a value of 2.5. Okay, so they're the same. And because they're the same, oh, I have to draw that again. That's all right. Because they're the same electronegativity, that means that neither atom in that covalent bond will exert a greater pull on the electrons within that bond. So we call that a non-polar bond. All right, just keep that in mind. That's a non-polar bond. Should become clearer to you in a couple of minutes. Let's look at this example here. Carbon, electronegativity value of 2.5, hydrogen 2.1. They're very similar electronegativity values, and I'll clarify that word similar in just a minute. So that electronegativity value probably would not do much in terms of the evenness of that sharing of the electrons in the covalent bond. So still something like that. All right, so the electrons in the covalent bond are being more or less shared equally between those 2 atoms. All right, now let's look at another example. Here we're looking at carbon and oxygen. Oh, I need to go back, sorry. Let's go here. Carbon, 2.5, oxygen, 3.5. Now, this is an important difference between those electronegativity values. So important, in fact, that it means we now have this type of situation. Oh, I should just draw carbon and oxygen. Now we have the oxygen with the higher electronegativity value is exerting a greater pull on those electrons in the covalent bond. So because this electron is now getting closer to the oxygen, it imparts a partial charge, a partial negative charge. And that partial negative charge is represented by this symbol, delta, and a negative. That means a partial negative charge is imparted on the oxygen because it's almost, but not quite picking up an additional negatively charged electron. Having said that, if we look at the carbon, carbon is almost losing its electron. Not quite losing it, but almost. So it is said to pick up a partial positive charge, which we refer to as delta positive. Now, because we have these 2 opposite charges here across this covalent bond, we refer to that bond as a polar covalent bond, otherwise known as a dipole. All right, so a carbon-oxygen double bond will be a polar bond, a polar covalent bond. All right, so what this means is that the electrons in the bond are unequally shared between the carbon and oxygen. An electron, or the electrons, are pulled towards the oxygen, which is the more electronegative element, that it has the higher electronegativity value, and that's indicated, the conferring of that partial negative charge is indicated by this delta negative. The electrons are being pulled away from the carbon, which is the less electronegative element, and that's indicated by this delta positive. Okay. All right, and we're nearly done. So let's look at this table. An interesting table, an important table, where the electronegativity difference between the two atoms is less than 0.5 units, which was certainly the case when we looked at the carbon and hydrogen covalent bond, for example. Then the bond type is said to be non-polar, and the electrons are more or less equally shared. Where the electronegativity difference is between 0.5 and 1.9, the bond type will be polar covalent, which means the unequal sharing of the electrons. The electrons in that covalent bond pull towards the more electronegative element. Now, if the electronegativity difference was greater than 1.9 units, then it is no longer a covalent bond. It means that the electrons are no longer being shared, they are being transferred. So when we have a transfer of electrons, that is loss and gain, we have, that is correct, transfer of electrons, the bond type becomes ionic. Electrons will be transferred from the less electronegative element to the more electronegative element. And that completes our lecture for tonight. So really well done, everyone. Great, always great to see that students are really revising the lecture material from one week to the next, because it helps so much moving forward when you can do that. It really, really helps in your understanding of the concepts as we come to them. All right, so now with tonight's lecture under your belt, you should be able to complete the tutorial questions from last week, which includes both last week's lecture on ionic compounds and tonight's lecture on covalent compounds. So remember, these questions are not assessed. There is an online quiz, remember, and you can just use that online quiz to check how you're going with these questions. But there is no weighting associated with these non-assessed quizzes. That doesn't mean that they're not important. They're still really important because, of course, these concepts will be tested or examined via your mid-semester test or via your final exam for the subject. So yeah, by all means, I understand when students actually start missing, skipping these non-assessed ones. That's fine, because of course you would be focusing on your, assessments for other subjects that do carry a weighting, but definitely keep them in mind. Also remember, the non-assessed quizzes do not close. They will stay open for the entire semester. Actually, they will stay open until after the final exam period. So there is no rush to get these done. And in fact, many students in the past actually don't do the online quizzes for these non-assessed tutes as they come up. They actually save that for the revision period. And then they'll tackle those quizzes. So that sounds like it's pretty useful. Oh, we've got a fun fact. Thank you. Neil Bartlett showed in 1962 when he made the first noble gas compound by mixing xenon with platinum hexafluoride. There you go. Very good. by mixing xenon with platinum hexafluoride. Thank you for that fun fact. In fact, that is a terrific initiative. If anyone finds any fun facts in their further reading, their further study, that would be fantastic if you can actually share that with us in the online class. That's great. Turnitin would not have liked that. No, Turnitin would only like that if you actually put that fun fact in quotation marks and included an in-text reference. Then Turnitin would be okay. But having said that, even though if you include a statement or statements in quotation marks, because it's a direct copy and paste, and you do include the in-text citation for that quotation, you're right in that it's not considered to be plagiarism, but it is not generally accepted in scientific writing to use direct quotes. Direct quotes should only be used very, very rarely if changing putting that sentence into your own words, in other words, paraphrasing that sentence, if that changes the meaning of that information, that's the only time you should use a direct quote. So that's a very good point. But that's great. Okay, so we have a question. Oh, all right, before I answer that, that's great. Just keep that question in mind just for a minute. I just want to mention another couple of things. So prac manual, so for those students that are not doing week-to-week prac classes, which means that you haven't received a prac manual, I have now uploaded the prac manual to Moodle. Have a look at a new folder called the additional information folder, and you'll find a copy of our prac manual. So don't print it unless you really wanted to. You will get a hard copy of this prac manual. All right, so what else do I need to say about this? So that's that prac manual for students that would like to do a bit of early reading up on the practice. Oh, excuse me. All right, so now let's field some questions about what we're planning. And of course, this means that we have to be, we meaning your lecturers, we have to be very, very creative in order to be able to keep delivering subjects. We have to be very creative. So let me just say, firstly, for anyone that joined in late, Melbourne Polytechnic, I received official notification late this afternoon. Melbourne Polytechnic will not be closing, Face-to-face classes will go ahead for many subjects, not for all of them. You've probably already been notified by a couple of your lecturers that certain subjects will now only be delivered online, but not face-to-face. That's certainly not the case for all subjects, particularly for those subjects that have very important practical skills training. Because while it would be easy to say, okay, everything's only going to be offered online, you would be missing out on probably the most important component of a subject and the most fun, I would have to say. It's the practical skills training that students really enjoy. And that's what we enjoy too, to be honest with you. Not that the theory is not important. Of course, the theory is important, but students do really enjoy the practical side of it, and the staff do too. All right, so let me think. All right, it'll come to me as we go through your questions. All right, so we've got a question here. Question about the prac weekend for students based outside of Victoria, and those states are in lockdown. Yes, not so fun fact. I've already spoken to one student about this. So we've got some interstate students that obviously and those states are in lockdown. So that's going to make it probably impossible for them to get here. So for those students, do not worry, because I will be organising an extra prac workshop. I can't tell you when, because it all really depends on how the coronavirus situation unfolds. So it might mean that your final mark for the subject will be just placed on a withheld, and that means that the subject will not be completed until such a time as that I can organise with you to make up those critical pracs to enable you to write up the prac reports. Another concession that's come from La Trobe recently is that for students where their final mark is on a withheld for something like Living Systems 1, that is not going to prevent them from enrolling in Living Systems 2. So you might know that Living Systems 1 is normally a prerequisite. So if you didn't pass that, then you couldn't do Living Systems 2. That will be waived. That prerequisite will be waived. So that's what I'm planning there. All right, so any grace for missing pracs due to coronavirus? Yes, definitely there will be grace for missing pracs. So even students that have just a mild illness, it could just be a bit of a cold or just something very mild, we are urging them not to attend at all. And if that is the case, then they will be given an exemption for missing those pracs. Yeah, so missing pracs, please just let me know. Please just let me know why you're missing pracs, you know, if you were scheduled to attend, and that will be fine. All right, so so if we haven't heard anything from lecturers, or hold on, I think I've missed some questions. Full-time work is unpredictable now. Yep. That's an understatement. Or can we switch to weekend intensive? Yes, absolutely. You can switch to weekend intensive. Oh, another word about the weekend intensive. So moving forward, we now must implement fully the social distancing, and that means that we can no longer have our normal number of students in the lab. That will mean that I'm planning to run an extra weekly prac class, most likely on a Monday, back-to-back pracs, so that we can implement that social distancing in the lab. The same thing will apply for to the prac intensive on the weekend. So I already had students split into 2 groups, but there will still be too many students in the lab. So I will definitely be introducing an additional prac intensive group. All right, yes. Now, if anyone would like to switch from weekly pracs to prac weekend intensive, by all means, please just send me an email to let me know what you're planning to do. All right, so I guess it depends on whether study is classed as essential travel as employment is. That's a good question. I can't answer that. I'm really not up with that at the moment. All right, let me just make this chat box a bit bigger so I can see your questions easier. All right. All right, so if we haven't heard anything from lecturers, we should presume face-to-face pracs are going ahead. Correct. So agronomy 1 will proceed tomorrow at the farm. What else have we got? Ag systems and tech. I still need to confirm. At the moment, as of right now, it is going ahead, but I must confirm with Stephen Burke that the social distancing can be implemented. So that's the question. So hopefully I'll have an answer for you on your tractor driving. Chemical users won't be a problem, but I do need to still confirm that with Kevin. But I'm, a little bit more concerned about the tractor driving. Yeah, a little bit worried that might not work. Okay. Winemaking 1, yes, we'll proceed face-to-face because we can easily implement the social distancing in both the wine tasting lab and the general lab. All right, another question. What is the reasoning for Melbourne Polytechnic remaining open when other institutions are closing? I cannot answer that, I'm sorry. That was not conveyed to me. All I know is that Melbourne Polytechnic, I can tell you, has no power whatsoever to make that decision. Melbourne Polytechnic is not a self-accrediting university, so universities can make those decisions. Melbourne Polytechnic is mandated by state government, and we have to be told, we are told by state government as to how we must proceed. So, sorry, I can't answer that. That's all I can tell you there. How do we know which group we are in? Oh, right. Oh, that will be posted. I will be posting that on Moodle. So that's for the prac intensive workshop. Yeah, so the dates and the times won't change, but your group, in other words, which lab you go to, that will be communicated to you before the prac workshop itself. All right, we've got another question. The agronomy class tomorrow is quite a large class. How can you practice social distancing in that environment? That's a very good point, and we've certainly had lots of conversations about that. Tomorrow's agronomy 1 class will only take place outside. It will not take place in the classroom unless there is a very small number of students that attend. If there are too many students to be able to use the classroom, it will only run outside. Okay. I'm on the weekend prac class, I see. Yeah. Okay, good. Good. Any other questions? Any other questions? There will be a change for some subjects, some changes in assessments. So, for example, I don't know if we've got any equine students that are on tonight. For one of the equine subjects, there is a prac exam. That will most likely change to a written exam. So there will be changes in some assessments. All right. Off topic, is it too late to enrol in additional units for this semester? Yes, it is too late. Yeah. Actually, sorry, no, I'm wrong. You can enrol in additional units before census date, but you must have permission firstly from the subject lecturer, because they need to tell you whether you can still catch up. You need to have permission from myself, and then those permissions, you will send them to our La Trobe course coordinator for final permission. So that's how that works. So let me know what subject you want to enrol in, and then we'll go through to the subject coordinator or the lecturer, if they are 2 different people, and make sure that it's not too late to catch up. All right, another question. Can I still purchase the lab coat from where you asked us to buy it from? Yes, you can. You can still purchase the lab coat. Absolutely. All right, do we have any other questions? Okay, are the weekend labs next week? No, they're not next week. So the weekend labs are, let's have a look in the prac book. Weekend labs are here, 2nd and 3rd of May, from 9 till 6. 2nd and 3rd of May, Saturday and Sunday, 2nd and 3rd of May, from 9 till 6. And you will be in, well, this will change, but we will use this lab in L109. We will use this lab in G118. And then, of course, I will need to run an extra prac group, an extra prac intensive at some stage. Okay. All right. Something that I should mention too, if you're worried about any of your subjects in terms of delivery or your ability to continue with the subject, remember census date. Census date is the 31st of this month. So you have a week, just over a week, or let's just say 1 week, to make up your mind as to whether you would like to proceed with one or more subjects. All right, any more questions? I don't think so. I think everyone's starting to sign out. Textbook readings. Textbook readings. Sorry, was that a question? Textbook readings. Any particular chapter? Are you talking about readings for Living Systems? For Living Systems 1? Yes. Okay, so if you have the textbook, you should easily be able to find the relevant chapter. Just look for the name of the lecture. The name of the lecture will indicate the chapter in the textbook. Yep. That is if you have the prescribed textbooks. Okay. You have? Wonderful. All right, I think that's all the questions. All right, thank you very much, everyone, for your wonderful attention, fantastic questions, as always. All right, please take care of yourselves, and I will keep you updated.
Thanks very much, Silvana.
All right, thank you. Thank you, everyone. I'll talk to you very soon. Oh.